So we are going to be learning a little bit about Kubernetes today. So we got this cool asking thing. We're gonna watch some Kubernetes with Pluralsight today. I don't know, the hackering problem that I was doing is just it's ridiculous. I mean, over time we're gonna come back to that, and I'm gonna try to implement it again. And just over the next few days, I'm going to be rehashing it and re-understanding it and stuff like that. But I mean, it's a hard, so hards are going to take some time for me to jump into. But that's what we're kind of doing here together. We're jumping into hards and seeing if we can actually get them done. So here we go. We're gonna jump into Kubernetes today, and hopefully we're gonna get our Kubernetes certification together. Hopefully we can do that. So it's gonna be great. Let's see what we can do.
The Application Design and Build for CKAD course here at Pluralsight. My name is Patrick. I'm a senior consultant and IT instructor from Germany, and I'll be your guide throughout this course.
If you already have a basic understanding of Kubernetes, this course is the perfect next step. You will not only gain deeper understanding of how Kubernetes runs your apps, but also learn how to build, package, and deploy those apps in a clean, efficient, and production-ready way. And here's what we'll cover. We begin by creating and managing container images. You'll learn how to write clean and secure Docker files, build and tag images with Docker, and push them to registries like Docker Hub or GitHub. We also take a look how to update your images safely when your application changes. And to tie it all together, I'll demo how to build and run custom images inside a Kubernetes pod. Next, we'll move on to the choosing the right workload. Kubernetes gives you multiple controller types, deployments, daemon sets, jobs, and more. And choosing the right one is key to building resilient apps. We'll compare these workloads, look at common use cases, and finish with a hands-on demo to help you make the right decision. From there, we'll dive into multi-container pod design. You learn how to use patterns like sidecars and init containers to improve observability, startup flow, and modularity. And again, we'll walk through a demo showing how to deploy a clean, production-friendly multi-container pod. Finally, we'll talk about working with volumes in Kubernetes. We'll explore ephemeral options like empty-dir, config map, and secret, as well as persistent storage with persistent volume claims and dynamic provisioning. We'll end the module with a practical deployment example that uses both types of storage. And throughout the course, I'll give you practical tips and hands-on demonstrations in a real Kubernetes cluster. Now, before we dive in, let me introduce you to Steve. Steve works at Globomantics, a fast-growing tech company that just adopted Kubernetes. He's a great developer, confident with containers, but now he's been asked to get one of the company's apps running in Kubernetes, and things don't go quite as planned. First, he writes a Docker file that's bulky, insecure, and bloated. Then he deploys a replica set instead of a deployment and doesn't understand why updates don't roll out. When the app starts crashing, it turns out he missed an important init step, and later when updating the image, he pushes it to the wrong registry, twice. Sound familiar? Steve's story isn't unique. Kubernetes is powerful, but it's easy to get lost in the details if you don't have a clear plan. And this course is designed to give you that clarity. By the end, you'll know how to build clean and secure container images, choose the right Kubernetes workload for your use case, design efficient multi-container pods, and use volumes to manage application data the right way. All without needing to learn it the hard way, like Steve did. One of these images. In Kubernetes, images are more than just a delivery format. They define how your application will run. Whether you're deploying a web app, a backend service, a sidecar, or even a system tool like a metrics exporter, every container in every pod is created from an image. That means if your image is slow, bloated, or misconfigured, it will affect the entire lifecycle of your app. Startup time, memory usage, security, everything starts with the image. Container images also make Kubernetes declarative. You define the what image to run, what version, and how many replicas in a YAML manifest. Kubernetes then handles the how, pulling the image from a registry and running it exactly as declared. This also means that changing the image version is all you need to deploy a new release. And that's why tags matter so much. If you're always using the latest tag, for example, you're not getting a predictable deployment. We'll cover this in more detail later, but just know that image versioning is critical for reproducible builds. Here's an example how to use the image in a Kubernetes pod. In Kubernetes, you will use a YAML-based file to declare what Kubernetes should do. In this case, it will deploy a single pod based on the MyAppImage version 1.0. And here's another example. Remember how I told you that versioning is crucial? Well, here's why. Let's say your app suddenly starts crashing in production. You roll back to the previous image version and it works. And that's the power of immutable infrastructure. You're not rolling back code, you're rolling back an image. And that means the environment and the app return to their known good state. And this kind of version control is a huge part of what makes containers and Kubernetes so resilient. Now, Kubernetes doesn't invent its own image format. It follows the OCI standard, which stands for Open Container Initiative. That means you can use tools like Docker, Podman, or Builder to build your images, and then store them in a registry like Docker Hub, GitHub Container Registry, or a private repository. Kubernetes simply needs access to that registry and the right image, path, and tag. In the earlier part of the course, we talked about container images and their role in Kubernetes. Now, let's dive into how to create these images, starting with the Docker file, the recipe for building your container. A clean and secure Docker file isn't just about making sure your container works. It's about creating something that's efficient, scalable, and secure. A poorly written Docker file can lead to slow build times, bloated images, and, worst of all, security vulnerabilities. Let's break down how to write a Docker file that's both clean and secure. At its core, a Docker file is a text file with instructions that tell Docker how to build an image. The structure is simple. From specifies the base image, run installs software or make changes to the container, copy or add bring files into the container, and cmd or entry points define the commands to run when the container starts. Let's go over a few best practices that will help you create efficient Docker files. Start with a minimal base image. You want to keep your images as small as possible to save bandwidth and storage. Avoid using full OS images when you can. For example, use Alpine or Slim versions of popular images whenever possible. Multi-stage builds allow you to use one image for building your app and another for running it. This helps keep your final image lean by removing unnecessary build tools from the runtime image. Let's take a look at some security considerations. Running containers as the root user is a security risk. Create a non-root user inside the container and run your application as that user. This helps prevent privilege escalation. Each package you install increases the attack surface of your container. Only install what you absolutely need for your application to run. Keep your base image clean and install only the required dependencies. Security vulnerabilities in dependencies are common, so you need to regularly update the packages and images you use. Tools like Docker Scan, or third-party tools like Trivy can help scan your images for known vulnerabilities. Let's talk about some optimizations to improve the performance of your Docker file. Minimize the number of layers. Each run, copy, and add command creates a new layer in your image. Try to minimize the number of layers by grouping commands together when possible. This reduces build time and the image size. And use caching wisely. Docker caches the layers of your image, which speeds up rebuilds. To take advantage of this, you should place the least likely to change instructions, like installing dependencies, at the top of your Docker file. This way, Docker can reuse cache layers when building a new image. And here's an example of a clean, secure Docker file. This Docker file starts with a minimal Alpine base image, uses multi-stage builds to separate the build environment from the runtime environment, runs as a non-root user to enhance security, and keeps the image size down by only copying the necessary files. Earlier, we covered how to write a clean and secure Docker file. And now it's time to bring that Docker file to life by building the image and tagging it. Docker's image building process is simple, but understanding how to optimize the build process and use tagging effectively is crucial for maintaining your workflow and versioning. So in this part, we'll cover how to build Docker images from your Docker file, the importance of proper image tagging, and how to push images to a registry. Once you have your Docker file ready, building an image is easy. The primary command you'll use is docker build. And here's a breakdown of the example command you see on the slide. The docker build and then the -t, so this flag specifies the tag for the image. The tag helps you version and differentiate the images. For example, version 1.0, latest, or any custom tag you prefer. Image name is the name you want to assign to the image. It's common to name it after your application. Tag, the version or identifier for the image, such as latest, version 1.0, etc. And path to Docker file, this is the directory containing your Docker file. In most cases, it's simply the current directory. And the current directory is referenced with a dot. So for example, docker build -t myapp version 1.0 and then another dot. This command will build an image named myapp with the tag version 1.0 from the Docker file located in the current directory. Let's take a quick look at the build process itself. Docker reads the Docker file. So Docker starts reading each instruction in your Docker file one by one, creating a new layer for each step. Docker caches the layers so that when you rebuild the image, it doesn't have to redo everything. It will only rebuild the layers that have changed, speeding up the process. And then the final image, once all layers are built, Docker will combine them into a single image. Once your image is built, it's crucial to properly tag it. Tags help you manage different versions of your application and control which image gets deployed in different environments. Best practices for tagging are use semantic versioning. Instead of just using latest, consider using a version number like version 1.0, 1.1, 2.0, or even version 1.0.0 minus beta, for example, because this allows you to track changes and roll back to a previous version if needed. You could also use environment-specific tags. You can use tags like staging, prod, or dev to specify which environment the image is intended for. This is especially useful when you have separate deployment pipelines for development, staging, and production environments. And you can tag with commit hashes. If you use version control like Git, it's helpful to tag your image with the current commit hash. This ensures that your images are tied to a specific version of your code, making it easier to trace back if something goes wrong. Once your image is built and tagged, the next step is often to push it into a registry, so it can be used by Kubernetes or other environments or other team members. To push an image to a Docker registry, for example Docker Hub, GitHub Container Registry, or others, use the following command, docker push. This command will push the image to the default Docker Hub registry. If you're using a private registry or another service like GitHub Container Registry, you need to specify the full URL of the registry. So for example, docker push ghcr.io and then the path and the image name with the version tag of your image. But make sure that you're logged into the registry using docker login before you attempt to push the image. Let's say you're working on an application and you need to make changes. Every time you build a new image after a change, you should update the tag to reflect the new version. For example, after fixing a bug, you might build and tag a new version with docker build, and then afterwards you push the new version of your image to your registry. And this helps you keep track of what's changed between versions and which versions are deployed in different environments.
We're gonna look into this a little bit more. So, alright, so we're gonna say, alright, Docker build, then Docker, is that just changing the text of the Docker file, or is it changing, or so how does Docker Hub hold? So does Docker Hub hold an image? And a Docker image is basically a virtual OS. Docker build, Docker push pushes it to Docker Hub, and then Docker build. So I need to do a Docker build, then Docker run to get a original container. Alright, interesting. So now that's out of the way, back to the motherfucking album.
Now that you know how to build and tag Docker images, the next step is to host those images in a registry. By hosting your images in a registry, you ensure that they are available for Kubernetes clusters, CI/CD pipelines, or any team member who need access to them. In this clip, we'll cover the role of a container registry, how to push images to it, and how to manage your images and access them securely. A container registry is a storage service where Docker images are hosted. It acts as a central repository that can store and serve your images to different environments, like Kubernetes or developers who need access to your application images. Popular container registries include Docker Hub, the default registry for Docker, and it's widely used. GitHub Container Registry, a registry provided by GitHub allowing you to store images directly alongside your codebase. Google Container Registry, which is Google's own solution for hosting container images. Amazon Elastic Container Registry, a registry provided by AWS for secure storage and management of Docker images. And Harbor, a common registry from the Cloud Native Computer Foundation. Let's start with Docker Hub, which is the most commonly used registry for public and private images. To push an image to Docker Hub, you need to follow these steps. First, you need to log in to your Docker Hub account. If you haven't created an account yet, head to Docker Hub and sign up. Once you have an account, use the following command to log in: docker login, and then you'll be prompted to enter your Docker Hub username and password. Before you can push your image, you need to tag it with your Docker Hub username. The format for tagging is docker tag myapp:version 1.0, and then provide your username /myapp:version 1.0. And after tagging the image, you can then push it to Docker Hub with the docker push your username /myapp:version 1.0. And this command uploads the image to your Docker Hub repository. Once the image is pushed, it will be available to pull from any machine that has access to Docker Hub. GitHub Container Registry is another great option, especially if you're already using GitHub for source control. It allows you to store and manage your container images securely. And here's how you can push an image to the GitHub Container Registry. First, authenticate Docker with GitHub by generating a personal access token from GitHub, and this will act as your password for logging in into the GitHub Container Registry. Once you have the token, log in to the registry using docker login command, as you can see it on the right example. You need to tag the image with the GitHub Container Registry format, which includes the ghcr.io prefix. And once tagged, you can then push the image to the GitHub Container Registry. And the image will be stored in your GitHub account and can be accessed by your Kubernetes cluster or any other service with access to this registry. Most registries, including Docker Hub and GitHub Container Registry, allow you to make repositories either public or private. Public repositories, these are accessible by anyone. If you're sharing open source projects, public repositories are a good choice. Private repositories, on the other hand, are only accessible to authenticated users. If your application is proprietary or needs restricted access, private repositories are ideal. To manage these settings on Docker Hub, for example, you can create a new repository with either public or private access directly from the website or from the CLI. And on GitHub, you can control repository visibility and permissions via the GitHub interface. One of the most important things to keep in mind when hosting images is versioning. Proper versioning allows you to track changes to your images and avoid confusion when multiple versions are in use. To ensure proper versioning, always tag your images with unique identifiers. And avoid using latest as the default tag for production applications, as it can lead to unexpected behavior. As you develop your applications and container images, there will inevitably be changes, bug fixes, new features, or dependency updates. When those changes occur, you'll need to update your Docker images and push them to your container registry. In this clip, we'll cover how to update a Docker image, best practices for managing versioning and ensuring a smooth deployment, and how to automate the process for efficiency and reliability. First, let's understand why updating your container images is so important. Container images are the fundamental building blocks of your Kubernetes applications. When you update your application, you need to ensure the image reflects those changes so that the containers in your Kubernetes pods run the updated version of your application. Common reasons to update an image include bug fixes. You found and fixed a bug in the code. Feature updates. New functionality has been added. Dependency upgrades. You need to update external libraries or frameworks. And of course, security patches. Critical vulnerabilities in libraries or the base image need to be fixed. How to update a Docker image. Modify your code or dependencies. So whether it's fixing a bug or adding new features, start by making the necessary changes to your application code or dependencies. After modifying your code, you might need to adjust your Docker file. This could include updating the base image, installing new dependencies, or altering the build process. For example, if you're updating the base image, you might change the from line from node:14 to from node:16. Once you made changes to your code or Docker file, you'll need to rebuild the Docker image using the docker build command. This command will create a new image tagged with version 1.1, representing the updated version of your application. And finally, push the updated image to your registry. After rebuilding the image, push it to your container registry, for example Docker Hub, with the docker push command. This ensures the updated image is available for Kubernetes to use. Once your image is updated and pushed to the registry, you can update your Kubernetes deployment to use the new image version. There are a few ways to do this, but most common is to modify the image field in your deployment YAML file. After that, apply the changes with kubectl apply and verify the update with kubectl get pods. You should see the pods being recreated, and your application should run with the new version. In your Kubernetes manifest, change the image tag to the updated version, like the example shows in the image section of your YAML manifest. It says version 1.1 on the right side, referencing the new image version of the My App application. To streamline the process of updating container images, especially for large teams or complex applications, consider using automation tools like CI/CD pipelines. Tools like GitHub Actions, Jenkins, or GitLab CI can automate the building, tagging, and pushing of new images every time you commit changes. You can set up a workflow where code changes trigger an automatic build, the image is tagged with the latest version, and the image is also pushed to the container registry. Kubernetes deployment is updated automatically, and this will eliminate the need for manual intervention and ensures a more consistent and efficient workflow. Now that we've covered the essential concepts of Docker images, it's time to see them in action. In this demo, we'll go through the steps of building a custom container image, pushing it to a registry, and using it in a Kubernetes pod. First, we will build a Docker image based on our application code. Then we will push the image to a container registry like Docker Hub. After that, we will deploy a Kubernetes pod using our custom image. And of course, we will verify if everything is running smoothly in our Kubernetes cluster. Before we start creating our Docker image, let me give you some short information about the environment I'm using. I'm using Docker Desktop on a local Windows server, using the Kubernetes feature enabled within the Docker Desktop functionalities. And right now I'm logged in into a Ubuntu, which is also running on my Windows client using the Windows Linux integration. Before we can create our Docker image, we need to specify the application itself. In my case, this will be a simple HTTP server. So in the directory I'm currently working in, I'm using Nano to create a file which is called server.js. And within this file, we need now to specify the application code itself. In this case, again, it's a simple web service. So we can save it and exit out of here. Next step would now be to create our Docker file. So we go ahead and say nano Docker file. And within here, we need to specify how the container should be built. In this case, we're using an Alpine node. We are copying the content of our server.js we just created, and we will expose the web service on the port 3000. So save and exit out of here as well. So we do have our application code, we do have our Docker file. Next step is to create our Docker image. Therefore, we will use the docker build command -t and then specify the image name and a tag. For example, my simple node, and we will use the version 1.0 in the same directory we are currently working on. Hit enter. And now you can see that it has finished building our Docker image. Now that we have built our Docker image, we can now use it locally with Docker Desktop and the integrated Kubernetes feature to define a pod and run the pod within your Kubernetes cluster. So next thing we need to specify is the YAML manifest for Kubernetes, where we specify that we want to create a pod based on this specific image we just created. So again, we need to create a file in this case. So for example, myapp-pod.yaml. And within this manifest, we're now specifying how Kubernetes should run the container. So this is how the manifest should look like. So we want to deploy an object which is called pod. It has a specific name, myapp-pod. We have a label. This is important for the next step. And we are referencing to our simple node image we just created earlier. So again, we can save it and exit out of here. And to make the app accessible in Kubernetes, we need to specify a Kubernetes object, which is called a node port service. Therefore, we need to create another YAML file, another YAML manifest, so that we can access the web service using the port we have defined. So once again, we're creating a new file. In this case, we call it myapp-service.yaml. And this manifest specifies the service for the application we want to run. In this case, it listens to the port 3000 and it will expose the content to the port 380, so we can save and exit out of here as well. And now the final step would be to deploy both of these manifests. So we are providing the information to our Kubernetes cluster, one, to start a pod based on the Docker image we created, and secondly, to create a service so that we can access the web service which is running within the container. So first step would be to use kubectl apply, and then with the -f we need to specify the file name, and in our case it's the myapp-pod.yaml, which should be deployed first. So we go ahead, say please do that, and the second step is then to use kubectl apply -f, and in this case it's the myapp service.
All right, let's rehash that a little bit because that seems important.
Use kubectl apply the port 3000, and it will expose the contents.yaml. And this manifest specifies the service for the application we want to run. In this case, it listens to the port 3000 and it will expose the content to the port 380, so we can save and exit out of here as well. And now the final step would be to deploy both of these manifests. So we are providing the information to our Kubernetes cluster, one, to start a pod based on the Docker image we created, and secondly, to create a service so that we can access the web service which is running within the container. So first step would be to use kubectl apply, and then with the -f we need to specify the file name, and in our case it's the myapp-pod.yaml, which should be deployed first. So we go ahead, say please do that, and the second step is then to use kubectl apply -f, and in this case it's the myapp service YAML. So now we can take a look. kubectl get pods. We can see that there is a running pod which is called myapp-pod, and when we hit kubectl get svc, we should see the second entry here that we have a node port service up and running. It has a virtual IP address, and you can see that it's exposing the port 3000 to the port 380. So finally, we of course now want to check whether we can reach the web service which is running within our Kubernetes pod. To verify whether our application is running, I switched over to a browser. I reached the localhost 380 port, and you can see that it tells us hello from Kubernetes. And that's exactly the text that we defined in the application code in the first step. Okay, cool. So now you have seen how to create a Docker file and how to use it in your local Kubernetes installation. But what if you want to push the image to a registry like Docker Hub because you want to share the image or you want to make it public available, for example? That's exactly the last step in this demonstration. I will now show you how to take your local Docker image and push it to a public repository. In my case, it's a Docker Hub repository I'm going to use. Before we jump into tagging and pushing our image to Docker Hub, let me just quickly show you my personal Docker Hub environment. There's no repository created yet. Just keep that in mind for later. Back on our Ubuntu machine here. So before you can push images to a registry, you need to log in. In this case, it's Docker login. You can see login succeeded, so we can proceed with the next step. So before we can push an image, you need to tag it with your Docker Hub username. And the format for this tag, I will show you this right now. So it's Docker tag, and then we choose the image we want to tag. In our case, we created the image which was called my simple node. Hope you remember. So my minus simple node, and we specify the version as well. And then next we need to provide our Docker Hub username and how the repository where the image is then afterwards placed should be called. So in my case, it's Patrick Rush 89, and then let's call it my app version 1.0, for example. So we tagged the image with the Docker Hub specific tag, and now we can go ahead and we can say Docker push, and then we can push the image using the Docker Hub tag we just have assigned to it. So Docker push, and then the tag and then we wait until it's fully uploaded into the Docker Hub repository. In the output here on the screen, you can see that it has successfully pushed the image to the repository. So let's jump over to Docker Hub one more time to see if we can now see a repository with the image as part of our Docker Hub registry. And there you go. I'm back on my Docker Hub. We can see it has created a repository which is called patrickbush89/myapp, and it contains one image.
All right, let's take a little bit of a break. Nice 30-second stretch break, just a minute stretch break. Just think about what we learned a little bit. Go think about it. Look over the side stuff and think, what did I just consume a little bit? Just take a little bit of time and think about what we just went over so you can get a little bit deeper understanding. All right, so after we just had some time to do it before, so we had the role of container in Kubernetes, we had writing a clean and secure Docker file, building and tagging image with Docker file, hosting images in a registry, updating images for application changes, and then we actually went through and actually doing that. So basically, the bulk of what this was all about was understanding the role of a Docker file, which is just, as we said, going back to this, the Docker file is just building a virtual environment. What it basically does is it uses your OS, takes the meat of it, and then says, okay, what else do you need? So it says, okay, you need Node, you need this, and then it builds this lightweight version of it and hosts that for you. And then we also talked about pushing changes to a registry, and that can be, there's many of them, but two big ones are Docker Hub and the GitHub Container Registry. So if you want to share your Docker file, just for if there's other people on your team, this is all about working in a team with people. Well, you're going to need this if you're working on a team in general, but Docker Hub is kind of like if you're working with, just a very loose-knit group of people. It depends on what your team is actually doing. If you're doing a little bootstrapping open source development and it's not really open source and you're just a team of people that need to share a Docker file, then you use Docker Hub. If not, I guess if you're doing production level code, you'd want to use GitHub Container Registry. So we're going to move on to module 2 now. After we understand that, we now have a thorough understanding of how Docker is used to help us build Kubernetes clusters.
As you start working with Kubernetes, understanding the different workload types is crucial for selecting the right one for your application. Each workload type has a specific role, from managing stateless applications to running services across your cluster or even handling background tasks. In this part of the journey, we'll cover what the main workload types are in Kubernetes, when to use each type, and how these workload types help Kubernetes manage your applications efficiently. Kubernetes offers a variety of workload types, each serving a specific purpose in application deployment and management. So let's start with the most commonly used workload types. Deployments are the most frequently used workload in Kubernetes. They're perfect for stateless application where each pod is identical and does not require persistent storage. Deployments allow you to scale your applications up and down with ease, automatically manage rolling updates and rollbacks, ensure that a specified number of pods are always running, and they are ideal for web servers, API, or any service where the state is not important and high availability is crucial. Replica sets are used to ensure that a specified number of identical pods are always running. While replica sets can operate independently, they are most often used as part of a deployment. The main difference between deployment and replica set is that deployments provide more features like automatic rolling updates. Replica sets are great when you need to manage a consistent number of pods, but don't need the extra features that deployments offer. Stateful sets are used for stateful applications. And these are applications that require stable, unique network identities, persistent storage that survives restarts. So stateful sets are essential for applications like databases or services that maintain state over time. They provide stable, ordered deployment and scaling of pods, which is crucial for stateful services. Other workloads you might encounter include daemon sets. These ensure that a copy of a pod runs on all or a specific subset of nodes in your cluster, ideal for background services that need to run on every node, like log collectors or monitoring agents. Jobs are used for running batch processes that run to completion, such as data migrations or scheduled cleanup tasks. And cron jobs are used for running tasks on a scheduled basis, similar to cron jobs in Linux, such as backups or periodic maintenance tasks. Choosing the right workload type is essential to ensure your application behaves as expected, scales efficiently, and is easy to maintain. Understanding the differences between deployments, replica sets, stateful sets, and the other workload types will help you make informed decisions when managing your Kubernetes clusters. Earlier, I introduced you to the different Kubernetes workload types. Now, let's take a closer look at deployments, replica sets, and stateful sets, three of the most common workload types in Kubernetes. Let's start with deployments, which are the most commonly used workload type in Kubernetes. They are best suited for stateless applications, where every pod in the deployment is identical. With deployments, you can scale your application by adjusting the number of pods running and perform rolling updates to gradually replace pods with new versions, ensuring minimal downtime. You can easily roll back to a previous version if something goes wrong. So for example, deployments are ideal for services like web servers, APIs, and microservices, where maintaining the state of individual pods isn't necessary. A replica set is similar to a deployment in that it ensures that a specified number of pods are running. However, replica sets don't offer the same advanced features as deployments, such as rolling updates or rollbacks. Typically, replica sets are managed by deployments, and you rarely need to use them directly. If you need to ensure that a specific number of pods are running, even when a node fails, replica sets handle it for you. And here's the key takeaway. If you want rolling updates, go with deployments. If you only need to manage pod replicas without complex features, replica sets might be enough. Now let's talk about stateful sets, which are designed for stateful applications that require stable identities and persistent storage. Stateful sets are best suited for applications such as databases, key value stores, or any application that requires stable network identities and persistent storage across pod restarts. So the key features for stateful sets: the pods receive unique and stable names that are maintained even if the pod is deleted or restarted. Persistent storage is automatically provisioned to each pod in a stateful set. And a ordered deployment and scaling ensure that pods are created and deleted in a specific order. So if your application needs to maintain state between restarts or requires a stable network identity, stateful sets are the go-to choice. So when should you use each of these workload types? Let's break it down. Use a deployment if you have a stateless application, you need to scale your application up or down quickly, and you want to perform rolling updates and rollbacks automatically. Use a replica set if you need to ensure a specific number of identical pods are always running. You don't need rolling updates, and you're fine managing replicas manually. And use a stateful set if your application requires persistent storage and stable network identities. You're running a database or any stateful services, for example. Understanding the differences between deployments, replica sets, and stateful sets is vital for managing your Kubernetes clusters effectively. Choosing the right workload type ensures that your application behaves as expected and can scale or recover without issues. Now let's dive into a workload type that's perfect for running background services, the daemon set. A daemon set ensures that a copy of a specific pod is running on every node in your cluster, or on a subset of nodes that match certain labels. The key benefit of a daemon set is that it guarantees that each node in your cluster gets exactly one pod running the same background services. New nodes added to the cluster automatically get the pod running on them, which is perfect for background processes like log collectors or monitoring agents. When you need to ensure that certain services are available on all nodes, daemon sets are the way to go. Daemon sets are primarily used for background services that need to run on every node, such as log aggregation, so running tools like Fluentd or Logstash to collect logs from each node, monitoring, tools like Prometheus Node Exporter or Datadog agents that gather metrics from each node in the cluster, network management, running services like Calico or Cilium for networking on every single node, and security agents, running security scanners or intrusion detection systems. By running these services as daemon sets, you ensure that no matter how many nodes are in your cluster, the required background service is running everywhere it needs to be. So you should use a daemon set when you need to run a service on every node in your cluster. The service should be available across all nodes, regardless of the scaling of your application. And you need a background process that should be deployed across the cluster for example, monitoring, logging, or security purposes. On the other hand, daemon sets aren't ideal when you only need the service on some nodes rather than all of them. For that, you might use labels or other controllers like deployments. Your service should be scalable based on demand, as daemon sets aren't designed for managing high numbers of replicas or scalable apps. In these cases, deployments or stateful sets might be a better fit. So it's important to remember that daemon sets are intended for specific use cases like background services, while deployments and stateful sets are for managing stateless or stateful applications, respectively. So if you need background services that must be run on every node, daemon sets provide a specialized solution that is simple and effective. But for apps requiring horizontal scaling or ordered deployment, deployments and stateful sets are way more suitable. It is time to look at cron jobs, which allow you to run scheduled tasks at specific times or intervals, much like cron jobs in Linux. A cron job in Kubernetes allows you to run a job on scheduled basis. Think of it as a cron expression that tells Kubernetes when to run a specific task. A cron job creates a job at a scheduled time, and each time the cron job is triggered, it will create a new job that runs to completion. For example, you can set up a cron job to run a script every night at midnight, or generate a report every Monday at 9 a.m., or perform system maintenance every weekend. And the syntax for scheduling is similar to cron in Linux. So if you're familiar with cron, you'll feel right at home with Kubernetes cron jobs. When you create a cron job, you specify the schedule, the frequency or time the cron job should run, expressed as a cron string. You define a job template, the definition of the job that should run when triggered, and cron job is responsible for creating a job at a specified time. The job runs the defined task and is marked as complete once it's finished. So the key points are: the cron job controller ensures the task runs at the specified schedule. You can specify concurrency policies or control how the cron job should behave if previous jobs are still running. And cron jobs can be configured to retain or clean up old jobs based on time limit or limit of the number of the completed jobs kept. Let me show you the cron job schema, because cron jobs are scheduled using a format similar to the traditional cron. So from left to right, you specify the minute, hour, day, month, and the day of the week for scheduling the jobs. So the left example here shows a schedule which runs the job every day at midnight. And the right example will run the job every Monday at 9 a.m. Cron jobs are ideal for tasks that need to run at regular intervals or at specific times, such as database backups, automatically backing up your database every night, log rotation, compression, or archiving logs regularly, report generation, running scripts to generate and, for example, email reports periodically, and system cleanups, running cleanup tasks to remove old files, temporary data, etc. Because cron jobs allow you to schedule tasks to run at precise times, they are a great fit for maintaining your Kubernetes applications and infrastructure. Let's take a look how to create a cron job in Kubernetes. Here's an example of a cron job definition. So basically it's again a YAML file for Kubernetes. And in this example, the cron job runs at midnight every day and starts a job that runs a container from the image myImage. And the job will restart the container only if it fits. Use a cron job when you need to run tasks on a scheduled basis. Tasks must run at a specific interval or a recurring schedule, or if you want Kubernetes to automatically handle the creation of jobs for you based on your schedule. A cron job, on the other hand, is not ideal when you need tasks to be executed on demand rather than on a schedule. For that, a job or a deployment would be more suitable, or if your task need to scale dynamically. For scaling tasks, use deployments or stateful sets. So cron jobs offer a powerful tool for automating and scheduling repetitive tasks within your Kubernetes cluster, whether it's for backups, log rotation, or periodic reporting. Cron job help you streamline and automate management tasks, reducing the need for manual intervention. Let's dive into jobs, which are used to run one-time tasks in Kubernetes. A job in Kubernetes is a resource that runs a pod until completion, ensuring that the task is executed once. Unlike cron jobs, which run on a schedule, a job is designed to execute a task one time, ensuring that the task is successfully completed before it terminates. Jobs are useful for tasks like batch processing, so running a specific process, such as a data transformation job, or database migrations, performing one-time database schema changes or updates, or script executions, running administrative scripts that need to run once, like creating a backup. When you create a job, you define the task to run, so the container or containers that should perform the job. You also specify the completion criteria, so the number of successful completions required for the job to be considered complete. And you can specify the concurrency policy, how the job should behave if multiple instances are running simultaneously. And when the job completes, it can exit successfully, so if the task completes as expected, or it can fail if the task encounters an error or doesn't meet the completion criteria. Kubernetes ensures that the job runs to completion and will retry if necessary, depending on how you configure the job. Jobs are ideal when you need to perform one-time tasks that should be executed to completion, succeed or fail once there's no need for repetition, unless you manually trigger it again, and be executed once across a single pod or a set of pods in parallel based on the job configuration. Some typical scenarios include backup tasks, so running a backup script for a database, migrations, running a one-time database schema update, or batch processing data in a batch and completing once finished. And jobs are not intended to run regularly. In this case, consider using cron jobs instead. Here's an example of a simple job definition in YAML. In this example, the job runs a container from the image myImage. The restart policy is set to never because you don't want the pod to restart once the job is completed. So Kubernetes will make sure the pod runs and completes the task before the job is marked as done. And you can configure how Kubernetes should handle retries in case of a failure using these fields. Backoff limit, the number of retries allowed before the job fails. For example, if you want the job to retry up to 3 times in case of a failure, you can set the backoff limit to 3. Completions set the number of successful completions required for the job to be considered successful. And parallelism is the number of pods to run concurrently. Now that you've learned about the major workload controllers in Kubernetes, deployments, replica sets, stateful sets, daemon sets, cron jobs, and jobs, let's bring it all together with a quick demo. In this demo, we'll walk through choosing the right controller based on an application's behavior, writing a manifest for the appropriate controller, and then finally deploy and verify it on a Kubernetes cluster. Let's imagine the following scenario. You're deploying a logging agent that needs to run on every node in the cluster to collect system logs and forward them to a central location. Think for a second, what kind of controller do we need? The right answer is a daemon set. Why? Because we want one pod per node automatically scheduled when new nodes are added. So let's open the YAML file and define a daemon set. But before we do that, let me quickly show you my Kubernetes environment. So I'm going to hit kubectl get nodes. And as you can see, I do have a Kubernetes cluster here running with 1 control plane and 2 worker nodes. So when we define a daemon set, what should happen is Kubernetes should roll out 2 pods, 1 pod on each worker node. To roll out our daemon set, we need to specify a YAML file. So we create a YAML file, for example, daemon set.yaml. What this daemon set does, it's basically printing out logs continuously. So we're going to save here. And now we can say kubectl apply. And now we can say kubectl apply -f and then our daemon set.yaml file. It says the daemon set with the name logwriter has created. So let's check with kubectl get daemon sets if we can find a daemon set. So we can see it has a daemon set, which is called log-writer. We do have a desired count of pods from 2, and we're currently using 2. So kubectl get pods shows us that there are 2 pods running, each on every worker node, because we defined it as a daemon set. And to verify the functionality of our log agents, we can hit kubectl logs and then one of the names. And you can see that it's continuously creating logs. Every 5 seconds, it's writing out the current date. So this is how you can define a daemon set YAML file and apply it to Kubernetes. But imagine a different scenario. If you need to deploy a stateless web application, for example, then you shouldn't probably go for a daemon set, right? You want to be able to use rolling updates for your stateless web application. So therefore, we need to use something that is called a deployment. And a deployment YAML could look like this. So we open up a YAML file again, call it deployment.yaml, and specify how our deployment should look like. So in this case, I want a deployment with 3 replicas of a specific image, and the image is called node-k8s-app, and then the specific version. In this case, it's the version 1.0. So we're gonna save out of here as well, and hit kubectl apply -f deployment.yaml. So in this case, Kubernetes is now rolling out a deployment based on the image we specified in the YAML file. And to make our web application available, we need to roll out a service as well. To do that, once again, open up an editor, call it servers.yaml or whatever you might prefer. And in this case, it's specifying a node port service to make our web service available on a specific port. So we're gonna save out of here again. Next step is to apply it to Kubernetes. So kubectl apply -f and then the service YAML. So now we can check kubectl get as we see. You see that we are running a node port service, and with kubectl get pods, we can see that in addition to our daemon set from earlier, we now have a web deployment up and running as well. And you can see that there are 3 pods as we defined in our YAML file. And to check the functionality of our web application, we'll quickly jump over to a web browser, open up the node port. In this case, it's 31966, and then we'll check whether we can see a message from our web service. Perfect. This is exactly what should happen. Hello from the Kubernetes web app. And for the third and final scenario in this demo, we want to take a look at how can we achieve the following scenario. So let's imagine you want to clean up a temporary directory every minute using a job, like a simple script, right? And so if you want to do this every minute, of course, you do not want to create a job yourself every minute, but we've learned that we can use cron job for it. So the final scenario here would be to create a cron job YAML to be able to run this script every minute. Therefore, we need to specify a cron job YAML file, cronjob.yaml. And in this case, we schedule a specific task every minute. So the schedule shows every minute. And the restart policy in this case is set to on failure. So it will only restart when something goes wrong. So save and quit out of here. Next step, of course, is to provide this YAML file to Kubernetes. So kubectl apply -f and then cron job YAML. So what should happen? We should now be able to check whether we have a cron job up and running, right? So kubectl get cron jobs. You see that we do have a cron job specified, the temp cleaner cron job here. With kubectl get jobs, we can see whether there is a job up and running. So in this case, it says no resources found. And this is because the cron job states that it should start a container running the job every minute. And in this case, unfortunately, we are not within the time frame of the schedule. But when we hit kubectl get pods and then watch, we can see that it now is starting a temp cleaner pod, and it will start a new pod every minute. So you can see temp cleaner, spanning, container creating, completed. So it will again and again start a new temp cleaner pod every minute. And to verify the functionality, let's just quickly check the logs with kubectl logs and then one of the temp cleaner containers. And then you can see the timestamp of the pod that has cleaned our temp files. Watch, we can see that it now is starting a temp cleaner pod, and it will start a new pod every minute. So you can see temp cleaner, spanning, container creating, completed. So it will again and again start a new temp cleaner pod every minute. And to verify the functionality, let's just quickly check the logs with kubectl logs and then one of the temp cleaner containers. And then you can see the timestamp of the pod that has cleaned our temp files. Now that you've learned about the major.
Alright, so I'm a little bit confused about the cron jobs, so we're going to get some more information on these. So, alright, so if I'm creating a cron job, does it get applied to deployments for the daemon set. Alright, so that's all we have for today. I gotta get going at 9:45, so we're not gonna have enough time to finish this because I'm gonna be stopping and starting a little bit. So that was Kubernetes for today. We got 59% of this course progress done. So application design and build for CKAD. So basically what we did was we had our Docker file. We learned about Docker files and writing them and uploading them to the registry and then updating images for application changes. Just remembering that you have to update that version file and just re-uploading them and then running Docker files. So you have Docker build, Docker run, Docker push. So I mean let's just rehash this.
Cover the essential.
And so I mean it's just so we have Docker build, Kubernetes apply, Docker build, and Docker login, Docker tag, Docker push. So Docker build, Docker push, Docker run. That's what we get. But that's all we got after this. And then after this, we have the choosing the right Kubernetes workload. We have deployments. So deployments allow you to specify the number of nodes. A replica set does that, but you have a fixed number of sets. And then a stateful set is what you do if you need to hold on to something in memory, like it uses a database. And then daemon sets are for if you need to have. So I mean, let's look at what's the difference between replica sets and daemon sets. What's the difference between replica sets and daemon sets? What's the difference between a pod, node, and service? I already Alright, so ensure a copy of a pod runs on every node. So daemon set is basically, we need to attach it to every single, ensure a copy of a pod runs on every node. One collector pod on each node. Automatically deploys one pod per node. Add a new node. So I guess a worker machine in Kubernetes cluster can be a VM or physical, runs the kubelet and container runtime. A pod, the smallest deployment unit, wraps one or more containers that should run together. Can die and be recreated, has its own IP address. So a node is a server that runs pods. So you have a bunch of pods in a node and a service. A stable network exposes one or more pods. A service. So would you only is a replica set and deployment for services. Alright, so basically these replica sets and deployments are not services. So it's having a group of workers. So a pod is basically a worker. Smallest wraps one or more ephemeral can die and be recreated. Has a pod. Think of a pod as your application process. A node is a server that runs pods. So you can have a bunch of pods on a node, and so each node would then have a replica set. So a deployment which runs stuff. You can have jobs. So that basically you have replica sets, deployments, state sets, replica. So what is it? It's replica sets, stateful sets, deployments, and so this is like not a service, but it's like you need some type of information to be saved on this. You need to I guess this is for like caching, and then daemon set is for the logging and security tools, and then you also have cron jobs that can also run, and Kubernetes can manage this. So Kubernetes manages a bunch of pods, nodes, handles. So it hosts nodes, and so it hosts nodes, and on that node you can have a bunch of pods, and you also need a service to expose those pods, and then you have a bunch of replica sets, deployments, and stateful sets to do some type of information with it. So last question we're going to ask, are deployments, replica sets, stateful sets, and daemon sets related to cron jobs or jobs in any way? Okay, so those are called controllers. So these are all controllers. Alright, so if you want to have a workload, so these are for like batch processing systems. Deployment, replica set, stateful sets, and daemon sets. These are what you use to run your batch processes on your application. And then you also have short-lived workloads. These are jobs and cron jobs. So app services that run continuously. Manage replica set, ensure pods are always running. Won't create a job. A cron job won't create a deployment. They both use pods under the hood. Both are managed by that. Alright, what? Alright, so basically if you have a node site, if you want to run your website, you have your node, and that creates the pods, and then well, because it has the node, and then onside the node you have a bunch of pods, and so these are these. right, so you use these. So we have these. So basically, this is talking about if you want to build a pod and get it up and running, you have these Docker files, and the Docker files basically can push the Maya app. It does the app and it has the YAML file. I don't know. I don't really think we need Docker at all. Docker was just there because you have to use Docker sometimes. But the real stuff is using Docker was just there, but kubectl myapply, that was just to get you up and running and have the idea of what you run a Kubernetes on. I guess Kubernetes uses Docker behind the scenes a little bit to create that virtual environment. And then you use kubectl, and so that's this. The first one was managing the container images, like what you need to use that is going to use the container. Inside a container controls a node. What is the difference between that's a Docker? Is it a Docker container or a Kubernetes container? Alright, and then so we have, and then this uses choosing the right Kubernetes workload. This is all about controllers. And inside controllers, we have deployments, replica sets, and stateful sets. And then we also have daemon sets that handles DevOps. I guess I call that DevOps stuff, just security, logging, all that extra stuff that happen. You know, it's the mom shit. It's what your mom wants to know about what you're doing. That's what I call a daemon set. Is your mom is a demon, and your mom manages all the crazy shit. Okay, your mom wants to know about what you're doing, where you're at. Are you good? Are you good? Is it safe? That's what a daemon set is. So you want to attach to every instance, everything you're doing. Your mom's worried about it. When you're growing up, she's at your school, she's at your friend's house, she's at your job, she's worried about your car, she's worried about your bank account, she's worried about what you're doing in your free time. It's the 6. That's why it's a daemon. It's got 6 things that she's worried about. 6, 6, 6. Or she's got 6 things. Each time she's worried about 6. In each of those 6 things, she's got 6. She's worried about for 6 different things within that thing, and then she's worried about it for 6 hours for each little thing, or 6 minutes. She worries about each little thing for 6 minutes, and that takes up 666 minutes of her day. She worries about you for 666 minutes a day. That's a 666 formula of your mother. So, and then we have cron jobs, and this is what she's going to do for each little thing. If this is where she has, alright, so every Monday I have to worry about this. Sometimes I have to run this job, or I have to call this person, this person, this person, this person, this person. And it's just tag team stuff. And then, so picking the right controller to deploy an app, that just tells us how to actually do this. But all we need to know is the theory behind it. We don't actually know how to do it. That's what you're going to Google and go into and pick apart one by one. So there we have it, folks. That's it for today. We did a quick 1 hour on Kubernetes, and we learned about Docker, how we use Docker in the Docker container registry. And then we learned about controllers, which is deployments, replica sets, stateful sets, daemon sets, and then cron jobs and jobs. So we actually learned a lot today in this 1 hour. We got a lot of information out of this, and I taught you about my mother, or your mother, or everybody's mother. So have fun. Peace out. Don't forget to like, comment, and subscribe. I love subscribers. I lost a subscriber because I uploaded some stuff. I gave him some content, and so I lost subscribers. So that's just part of it, is building this is what my channel does. My channel does music. My channel does a lot of things. It's just my life. This is what I'm into, and I'm building my channel. This is what my channel does. My channel does a lot of things. I like music. I like making music. I like programming. I like actually programming. I don't know. That's basically what I've been live streaming, is me making music, uploading music. I talked about music a little bit. I talked about the Drake album. So I'm going to be putting on this and trying to make more 1 hour shows. So this was like an extra long edition. I did some more information I added to it a little bit. So I don't even think I'm copyright infringing. I'm adding a little bit to the course while I go through it. So we're trying to get that Kubernetes certification. So that's just what's going on. So yeah, thanks for tuning in.